So yesterday we talked about, or introduced the idea of inverse relations, and then we touched on this idea of inverse functions. Let's look at inverse functions in a bit more detail. So the actual symbol for inverse functions is the negative one. Now, so it doesn't mean to the power of negative one. We're not talking reciprocal. Yeah? So on your calculators, you'll notice on the trig keys, you've got tan to the negative one and cos to the negative one and so on. Well, they're not the reciprocal ratios. They're the ones you press when you want to go backwards and find the angle rather than the ratio, because it's talking about the inverse function. So f with a negative 1 there means inverse function. Now, thing about inverse functions, if we take the composite of both the function and the inverse function, because inverses should cancel, we should end up with x. And it doesn't matter which way we go. If we substitute the inverse into the original function, or the original function into the inverse function, we should end up with x. So let's try one. Let's say our function is x minus 2 over x plus 2, which would be, a hyperbola, wouldn't it? Shifted, what's that one going to be? Across 2, up 1? I think it's across 2, up 1. But anyway, it doesn't matter. We don't really need to know what the picture looks like for this. Let's work out the inverse so then we can substitute in and see if it works. So we swap the x and the y's round, and I want to make y the subject. So a little bit of algebra there to do, but eventually we get to the inverse, 2x plus 2 on 1 minus x. And it is an inverse function, because yet again we've ended up with another hyperbola. And we know our basic hyperbolas are going to be functions. All right, let's sub the function into the inverse. So everywhere I see an x, I'm replacing it with x minus 2 on x plus 2. But I've ended up with fraction on fraction, but the denominators are the same, so that's easy to resolve. I'll multiply both top and bottom by x plus 2, and eventually it comes down, and sure enough, it turns out to be x. So that's when I substitute the function into the inverse. The reverse should be true as well, so let's have a look at that. If I substitute the inverse, so 2x plus 2 on 1 minus x, sub that into the original function, multiply everything by 1 minus x, and once again, yep, it does come down to be x. So it satisfies our little rule there. Domain and range. Remember we said they swap around. The domain of the original function becomes the range of the inverse and vice versa. So if there's a point AB on the original function, because basically we're swapping the x and y's around, then the point BA should be a point on the inverse function. And so thus, what I was just saying, the domain of the original function becomes the range of the inverse, and the range of the original function becomes the domain of the inverse. So let's do an example here. So we've got e to the power of x, an exponential curve. And there's the picture over there, our basic exponential, e to the power of x. Well, we know the domain of our original function is all real x. And the range would be y is greater than 0. The inverse function, so a bit like this I suppose is what we're saying. Okay, now I'm highlighting, I'm finding the inverse. I swap the x and the y's around, and to undo exponentials we log both sides, so we end up with y equals the log of x. So the domain of the inverse, log x, is x is greater than 0, because the range of the original one was y is greater than 0. And the range should end up being all real y. And sure enough, if we were to draw in our log curve, yep, we can see the domain and range satisfy that. I've also drawn in y equals x, you'll notice there, just to again highlight that they're reflections of each other in the line y equals x, if you were to draw them. Now, when you think about it, we said in order to have an inverse function, we had to have a one-to-one relationship. Most functions don't have that. I mean, look at our parabola. It's not one-to-one, it's many to one. No, many to one. The hyperbola's okay. Yeah. The cubic's okay, and obviously the circle can't have an inverse function because it's not a function in the first place. Right? The first criteria is it has to be a function, and then the inverse has to be a function as well. So what we end up doing is we restrict the domain of the original function to create a situation where the piece of the function that we're playing with would have a one-to-one relationship. You basically want to choose a domain so the piece of the graph you've chosen is always increasing or always decreasing. In other words, it never turns and comes back down, because as soon as it turns and comes back down, it's going to fail that horizontal line test. So we want to get a piece that's always increasing or always decreasing. So let's have a look at our parabola. There's y equals x squared. Now, we know, yes, the domain for that's all real x. The range is y is greater than or equal to 0, but it doesn't have an inverse. It fails the horizontal. So we want to restrict our domain. So we want to get a piece of that parabola which is continually increasing or continually decreasing. And ideally, we'd like to capture as much of the range as possible. Now for this one, it's actually possible to capture all of the range. Because if I was just to pick x is greater than or equal to 0, if I restrict my domain to that, so I've just got the right-hand side of the parabola, well, that would satisfy the horizontal line test. And in fact, I've got the whole range as well. So the range will remain at y is greater than or equal to 0. So my inverse would be x to the power of a half, or the positive square root. The domain is x is greater than or equal to 0. The range is y is greater than or equal to 0. Let's draw it in. There's y equals x. So it would be the reflection, and I'm just using the right-hand side of the parabola now, but it would end up looking like that. It's very much like, I guess, when we're talking about semicircles, because the circle is not a function, but we break it into the positive square root would be the top half, negative square root would be the bottom half. So we've split it into two functions. It's the same sort of idea. I suppose the general rule, we try and keep it positive if we can, and try and include 0 if we can. But I mean, it wouldn't be wrong if they simply said find an inverse function. It wouldn't be wrong to do the negative square root. It's just a different function. Okay, this gives us another way to find range. Because remember, we just said the domain and the range swap over, and sometimes people find it easier to find domain than range. So instead of finding the range of the function, find the domain of the inverse function. So, well, y equals x squared. Not that that's a real hard one, I guess. But I'll change to capital X and Y so I don't get confused about which one's the original function and which one's the new function. So if I swap the x and y around, capital X equals capital Y squared. So I get capital Y equals the square root of x. Now, if I was to ask myself, what's the domain of that, I'd say, oh, well, whatever's under the square root sign has to be greater than or equal to 0. That's the domain of the new function. Therefore, the range of the original function must have been y is greater than or equal to 0. So that's just an alternative way. Let's try another one. Not that it's much different, really. I've just shifted it up 3. But okay, y is equal to x squared plus 3. Swap the x and the y's round. Make y the subject. So now we've got, oh, hang on, square root of x minus 3. So we know x has to be greater than or equal to 3. That's the domain of the new function. Therefore, the range of the original function, y is greater than or equal to 3. Y is the absolute value of x plus 2 minus 5. Okay, we've got to be careful with this one because of the absolute value. So x is equal to the absolute value of y plus 2 minus 5. So x plus 5 is the absolute value of y plus 2. So x plus 5 would be greater than or equal to 0, because we're saying x plus 5 has to be a positive amount, because the answer is the absolute value of something. And so the domain of the new function would be x is greater than or equal to minus 5. Therefore, the range of the original function, y is greater than or equal to minus 5. The semicircle. Well, let's pretend we didn't know it was a semicircle. Oh, this unusual shape here that we have no idea what it looks like. Square root of 4 minus x squared. Okay, swap the x and the y's around. I get x equals the square root of 4 minus y squared. I want to make y the subject. So I'll square both sides. I end up with y is the square root of 4 minus x squared. Oh, hang on. It's exactly the same. But with this one, I'm now finding the domain rather than the range. So I can say, oh, well, the domain of the new function is x is in between minus 2 and 2. Therefore, the range of the original function, oh, hang on, That won't work, because now let's think about what the shape actually is. It's the top half of the semicircle. So, not going to work in 100% of cases. You've got to have a bit of a think here. Domain of the new function, so I can't just say the range of the old function is in between -2 and 2, because look at what the original function was. I know I've got to get positive numbers. So I know y has to be greater than 0, so it's actually only going to be in between 0 and 2. So be careful if you're going to use this method. Let's have a look at the hyperbola then. Swap the x and the y's around, eventually make y the subject. So if I was going to play with the domain of that one, we'd say, oh, well, it's all real x, except x can't be 1. Therefore, the range of the original one, all real y, except y can't be 1. All right, so 5G, time to play with inverse functions.